we shall take up a problem from the concepts of shear force and bending moment in this video. Now, the system is given like this. Here it is shown. There is a beam on which there is a uniformly distributed load of 3.5 kilonewtons per meter, and then there is an arm like this, this CDE, and at E there is a 3 kilonewton force acting. Okay. And we are supposed to find out the shear force and bending moment diagram, and then we have to figure out what is the maximum value of bending moment that is occurring and the maximum value of the shear force that is occurring anywhere along the beam. Okay, so now the most crucial thing in this problem is this force which is acting through this arm on the beam. Generally students, when they see this, they get confused. So first, whenever we see such configurations, we will have to do one shifting of this force to this point. Okay. Now then we can get rid of this basically. Okay, so let's do that first. Now this 3 kilonewton force acting here is equivalent to, remember we have studied the equivalence of forces, so this is equivalent to 3 kilonewton force acting here along with a moment which acts in this direction. Let's say this is m, and that's the compensatory moment. If you remember, whenever we shift a force parallelly to another point, a compensatory moment, couple moment comes into picture. Now what is that moment? That moment we can write here will be equal to this 3 kilonewton times the distance which it has traveled is 0.9, right? 0.9. So this is like 2.7 kilonewton meter. Okay, so this is the compensatory moment which acts. So once we do that, the system becomes as if this portion is gone, this arm, and this force and the moment are acting at this. So that is the setup. I will draw it here for drawing the SF and BM diagram onwards. So let's draw the beam. So this is the beam. Okay, so this is the point A, this is the point B, and now as the first step, what we generally do is we will remove these supports, okay, and we will replace those supports by the reaction that those supports are actually providing. So if RA and RB, okay, so that's the reaction force, and then we have this uniformly distributed load on the whole beam, and this is 3.5 kilonewton per meter. Okay, and then then we have these forces. So one force is at this location, it's of 3 kilonewton, and a moment, okay, and a moment acting, that is 2.7 kilonewton meter. Fine. So this is the setup. Now once we have handled this portion, now it's as simple as any other normal shear force bending moment diagram problem. Okay, so then what we should do is next step, as we always do, so we should look for force, area, or material discontinuity. Okay, now if you see this, so there is only one kind of discontinuity, that is the force discontinuity at the point C. Okay, so this point is C. So and then so that's how we are splitting this full segment, full beam into two segments. Okay, now so then segment by segment we will try to evaluate. Okay, so let's draw even the axis for drawing the shear force. So now suppose this is the axis for shear force drawing, and this is the axis for bending moment drawing. This is bad. Shear force axis, bending moment. So here we will draw the shear force, here we will draw the bending moment for segments A, B and C, A, B and C. Okay, so as the first step, we should what we should do is to we should find out the reactions, right? Let's find out the reactions RA and RB. Okay, now how to find RA? So we have to take, say, suppose moment about the point B, so that should go to 0, right? So let's say how to do that. Say R, so let's say we will write R, sorry, RA times this full distance. Full distance is how much? 1.5 plus 0.9, 2.4 plus 0.6, so 3 meters, right? So this is 3 meters in the clockwise direction, plus anything in the same direction? No, I think all other things are in the opposite direction. So then that minus 3 kilonewton times, what is the distance here? It's 0.6, right? So this is also in the counterclockwise direction. So this is in the counterclockwise direction, that is why this negative sign. Okay, and then what about this one? This couple moment, this again is counterclockwise direction, so minus 2.7 kilonewton meter, and then because of this uniformly distributed load, the thing is minus 3.5 is the density times the full what is the total length of the beam? It's we calculated 3 meters, right? Yeah, so it's 3 meter. And where is it acting? So the equivalent is acting at a like midpoint, right? So it's like 1.5. Fine. So that's the full thing. So from here, if you solve, you get RA. Let me see how much it has come. It's 6.75 Newton. Okay, so RA is evaluated now, and using the similar process, okay, by taking moment, if you take moment about A, or by summing all the vertical forces, whatever you do, so from there you can get RB, and it will come out to be that also for 6.75 Newton. That's quite obvious, because the loading is symmetric, because earlier if you see, this 3 kilonewton was acting exactly midway on the beam, so that's why the reactions are exactly same. 6.75 kilonewton on both the supports. Okay, so one step is done, so I'll call this a step maybe. Okay, then going to step 2, that's for segment say AC. Now what we should do to draw the shear force and bending moment diagram for AC. As usual, it's the most general thing, we draw the free body diagram, right? So the free body diagram, so we come to any arbitrary section like here, any point, okay, at a distance x from this end, and then we cut the beam from there. So that means we have a segment of the beam of length x, and here we have this uniformly distributed load, and here we have the reaction Ra. Okay, and we know the conventions. So the convention V, positive V is shown here, and similarly the positive M is shown here, because we have kept the left side of the beam and we have thrown away the right side. So this is the positive convention. So then for the shear force, okay, so for SF, what we should do, summation of all the forces in the y direction should be 0. So summation of all forces in the y direction should be 0, considering this vertical direction to be y. So let's write that. So let's say V, then minus RA, okay, which is known to be this, then plus whatever this is, so 3.5 is the density times x, fine. So that's these are the only forces, right? Yeah, should be 0, implies V should be equal to Ra is 6.75 kilonewton per kilonewton minus 3.5x. So this is our shear force for the segment AC. Okay, then get the limits. So at x is equal to 0, V, that is at A, obviously it will be 6.75. Then at, and it's a linear equation, so simply we have to evaluate at another point, that is at x is equal to which is this point. Up to this point it will be a single line, so this distance is 0.9 plus 1.5, so 2.4. X is equal to 2.4, sorry, 2.4. So at that is at V at C, right? So V at C will become 6.75 minus 3.5 times 2.4. So implies VC will be equal to minus 1.64 kilonewton. Fine. It's 6. I think it's 6.5. So let me. Yeah. So it's 1.65 kilonewton. Okay. So we now know the points. So let's say here it's 8 point something. What was that? Sorry, 6.75, and here it's minus 1.65. So it's a line between these two. So it's like that. Okay. So this is the variation of shear force up to this point. Now we can draw the bending moment diagram. Okay, so for bending moment, still we are in the segment of AC, right? We have calculated shear force, now we are going to do the bending moment. For that we have to just write a sigma m about this point O, whatever that point is, moment about O should be 0. So what's the equation? Say m, the positive m which we have chosen through convention, is the counterclockwise, minus Ra times x, it is in the clockwise direction, then plus the moment due to this, what is the weight? It is 3.5 times x is the weight, but it is acting as if it is acting at the center of gravity of that uniform distribution, so that will be x over 2, right? So that should be equal to 0. What does that mean? Implies m comes out to be so this is 6.75, right? So 6.75x minus this is 1.75 x square is the equation of m. Fine. Now, so then again we have to find out some limits. Okay, so at x is equal to 0, at x is equal to 0, what's the moment? So m at a is equal to 0. Fine. Then what happens at x is equal to 2.4, right? So at x is equal to 2.4, we get ma is equal to, so just substitute 2.4 here in this place, and you will get the value of 6.12 kilonewton meter. This is not ma, sorry, so this should be mc, right? But see, this is a quadratic equation, that means it's a parabola, and because there is a negative sign over here, it's a downward looking parabola. Okay, so that means there is some point we do not know yet, that there could be a maximum occurring between this zone also, that we don't know. So that you can get by seeing where the slope of this curve is getting 0 by doing dm over dx equal to 0. So that will give you 6.75 minus it's like 3.5x, so that is 0, implies x will come out to be 1.9286, sorry, 86. So this is the location. Let's see, 1.92, so this will be somewhere, this is 1.5, so here somewhere here the maximum will occur. Okay, see, one point to be observed is wherever this dm by dx, you remember dm by dx is nothing but your v, also shear force. So instead of doing this differentiation, you could have directly checked where the v shear force is going to 0, and so that actually coming to the same equation you see here. So you could have seen that wherever this shear force is coming to 0, so that location is the location where the bending moment will be maximum, and it's a parabola. So let's draw something like this. So it's parabola with a maximum at this location. So this point is how much did we get? 6.12. This is 6.12, and this point is at the maximum. Okay, we can calculate that also. Then at sorry, at x is equal to 1.9286, we get m at what that point is, a, b, c, you can say d and e are here, so we can say the point g. Okay, now at m at g will be equal to 6.5089 kilonewton meter. Fine. So this is the value at maximum 6.505089. So this is 6.51. Okay, kilonewton meter. So at this point, this is the top. Yeah. So following the exact, so now we have finished for the segment, both the bending moment diagram and the shear force diagram for the segment AC. So exactly in the same way, step 3, if I can write. So step 3, that is for segment CB. Okay. So again, you have to follow the same thing, and then you can do you can go to a cross section here and cut it somewhere, and then again you have the option of keeping this left side as the free body or the right side as the free body. Obviously, if you keep this left side, there are a lot many forces. So what I would prefer is I would keep the right side as my free body and leave the left side. um, I'll throw away the left side. So suppose this is the free body, and here you have RB. Fine. And then this uniform again is acting 3.5 kilonewton per meter. Fine. And but then there was a point here which was our point C. So we can, it's always a nice practice to calculate x from here, so that this one, this distance will become, how much was that? It was 0.6, right? So this will become 0.6 minus x, so that the curve which you will get will be very easy to calculate. All the limits calculation will be easier here. Fine. So exactly you have to do for the same thing for the shear force. So let me draw the positive convention for the moment and for the shear force. So that's V. Okay, so when you calculate for V, so you have to write that, so V upwards plus RB upwards minus this one is this is 3.5. okay, so this is 3.5 times 0.6 minus x. So that's the load which is coming here. Okay, so that should be equal to 0, implies V is equal to 3.5 into 0.6 minus x minus RB was 6.75. It was 6.75, right? Yeah. So 6.75. And you can calculate limits, right? So if you calculate limits, what you will get is the shear force at B. So let's calculate the at limits. At x is equal to this one is 0.9, sorry, 0.6. I'm writing again 0.6, right? So this term simply goes away and you get v, that is at b, is equal to minus 6.75. Fine. So here somewhere you will get this much also, the distance, yeah, so here somewhere. Okay, then at x is equal to 0, if you put x equal to 0, so 3.5 into 0.6, so now v at so what, I'll just tell you one thing. Here we wrote v at c, right? Where did I get? So v at c. So generally there's a practice that you write v at c minus. That means just before this c point, from you are coming from the left side, and just before that it's the value in the limit. Because on the right side there will be here there will be a discontinuity because of this 3 kilonewton force. So that's how you will have to write Vc plus now. So you will get V at C plus. Okay, so that will become uh, so 3.5 into 0.6 minus that will come out to be how much is that? Minus 4.65 kilonewton. Okay. So and then similarly you can, so let me draw that. So here you will actually so 3 what is that point, it was VHC was 1.65, so then minus 3 basically. Okay, so there is a discontinuity of 3 kilonewton, and that is how it is coming to be 4.65. Okay, so there is a drop of this 3 kilonewton, and then yeah, so here it's a, so this is minus 6.75, here it is minus 4.65, here it's minus 1.65, etc. Fine. So that's the diagram for the shear force completely. So that is the shear force diagram. And similarly, if you do for the bending moment, so you will get there is a jump of a bending moment here. Okay, in fact this zone it's not defined, I shouldn't be drawing this, but I'm just drawing to make it look good, nothing else. And here there is a again a parabola like this, and this value will come out to be 3.42. Fine. So this is how your shear force and bending moment should look like for the system which was given to us. Okay, I'm not calculating this shape here because the video is getting anyway very long, but I think it's quite clear what you are supposed to do. Okay, so that means you are just you should write the moment equation about this point, and then that is it. Okay, so I think and I hope that it's clear how to do the shear force bending moment diagram for such a system and how to handle such brackets. Great then. So we will see with another problem in the next video. Thank you.